Hi, everyone. I'm Doug Black at InsideHPC. We're at the ISC 2025 conference here in Hamburg, Germany. And we're at the Hammerspace booth, the data platform company. With me is Molly Presley. She is CMO of Hammerspace. And Gary Greider, who is, your title is Senior Advisor for Computing Technology at Los Alamos National Lab. Now, at a high level, describe the demo that Hammerspace and Los Alamos are showing here at ISC.
Sure. So the demo is really about when you produce data that has such large gravity that you don't really want to ship the data very far to process it. And so instead, you want to ship the process to near the data. And there's standard ways of doing that through the Apache ecosystem. And so we've worked with Hammerspace to get all that infrastructure working inside of pNFS, which is this open source standard way of doing data management. So it's trying to merge two standards in a way, a set of standard Apache analytics ecosystem pushdown technologies and the pNFS technology that they provide.
And I would just add to that Hammerspace is very committed to developing pNFS, and the use case for it is very broad as far as delivering high performance as well as access to distributed data sets, and then being able to show this added functionality now of being able to simulate in place and reduce the amount of data movement wherever possible, all in this standards-based architecture, is really game-changing in how HPC workloads are being architected.
Okay, so now you mentioned a query pushdown use case using standard pNFS in the Linux kernel. Explain how this really improves simulation workloads compared to traditional data analytics.
We don't really do conventional data analytics in HPC so much. Moreover, we really do data, analysis using visualization tools primarily. And so people want to look at large amounts of data, a petabyte per time step, 10,000 time steps, 10 exabytes. It's a lot of data. And today, the way we would do that is we would pull each petabyte into a supercomputer that has a petabyte of DRAM and look for features we're interested in and visualize those. But that's pretty expensive. You're using a $250 million supercomputer to do data analytics on. You're moving a lot of data, and that takes a while. It's very expensive, very slow, and it's very energy consuming. Um, if you can push that, push a reduction step to close to the data and only pull back the data you need, sometimes it's 2 orders of magnitude less, sometimes it's 6 orders of magnitude less data that you're moving. So it's way faster, it's way more efficient. But it also allows you to use a very much smaller system to do your analysis on. So instead of having to have a $250 million supercomputer to do your analysis on, you can do it on a system that's 2 or 3 orders of magnitude smaller. And you're not tying up your large resource to do this. You can do it on a much smaller resource.
Talk about in the demo how it shows storage as an active participant in data pipelines, in practical terms for researchers running large simulations.
So the way it works is a simulation is run for a scientist. The scientist knows what it's doing. It's a large set of data, a bunch of variables, pressure, temperature, momentum, velocity, all sorts of things, and they know the phenomenon they're looking for, and they know sort of the characteristics of the phenomenon they're looking for, and so they can write a query that says, "I'm only interested in where velocities are larger than something." And we can, instead of pulling all the data back and sifting through it and finding that for them, we can just push that query down to right next to the storage and have it run as the data is read off of the storage. And only the answers, that pass that query get passed back to the application through the network. And so it's very much a domain scientist thing, but it's for any domain science, right? Every science has some sort of a feature that they're looking for. And usually it's a very small amount of the data that they simulate. So you get this reduction, and they love it because it's faster. And in fact, in some cases, they can even run the analytics on their workstation. They get that much data reduction. So they don't have to schedule time on the supercomputer and come in next Thursday and get the answer. They can get the answer right away.
The value of putting this all into pNFS, that we want to get into an open standards-based architecture where the file interfaces, the way scientists are used to interacting with data is natively presented to them instead of having to go off and ask somebody in the IT team to help them get access to the data or connect them to the storage system. This is a native standards-based access to make it very easy for them to connect.
Now, given that Los Alamos simulations handle critical national security scenarios, what does broad compatibility using standard pNFS and open analytics tools really mean for research institutions?
Hard question. So I think it's our longevity, right? We've been around for a long time, 1941, and we first started doing a lot of computing in 1943. Much of the physics that we use is that old, and some of it is invented yesterday. And so we have to keep data around for a really long time, longer than any company probably will ever be alive, right? Because our data and our secrets and our methods will live on long after we're all gone, right? And so we really need to stick to standards and stick to open protocols and things like that, because the longevity of what we do is so long, and the secrets remain secret for so long because it's not like taking a picture and now somebody's moved. It's physics, it's physics understanding of materials and how they act, and that stuff lives forever. And so I think that's, it's not necessarily so much the security part of it, it's the longevity part of it that forces us to try to do things in open and standard ways. And of course, promoting communities helps you get longevity. And it helps you get longevity in affordable ways, right? Because more people can participate. So it's in almost every way, it's good. But longevity is what drives us.
Now, Molly, tell us about Hammerspace, its position in the data platform industry.
Yeah, we have a broad commitment to bringing standards into our data platform. So what that means is standard interfaces to the storage, using standard networking, using functionality that's built into Linux, which won the operating system war years ago, and making it very easy for any data creation, human or maybe a supercomputer, maybe it's a sensor. All of that data can live in a single platform and be accessed easily across standard infrastructure. And certainly in this world where in HPC, and we're a supercomputing show, we've cared a lot about performance. That matters a lot. But now as data sets are more distributed and AI users are now using them in addition to the supercomputing users, making it easy to access that data across different applications, different locations, different humans is really what our platform approach is about. And then the commitment to pNFS, which we're demonstrating here at the show, and was an early kind of thought, Gary was an early thought leader in, is about making it where you can have just NFS connect to all of your data, and you don't have to design applications and workflows to access the data, where legacy HPC, you've had to kind of purpose-built specialized infrastructure to access data. We're trying to make it as easy and standard as possible. So Hammerspace is kind of bridging the gap between supercomputing and AI by having a data platform designed for both.
Gary, tell us what the demo is actually showing in real life.
Okay, so it's an asteroid impacting the Earth simulation. So it's a simulation of the Chicxulub event that happened in the Gulf of Mexico, and essentially, we study the incidence angle of the asteroid and the size of the asteroid, and how it goes through the water. When it hits below the water, it gets all the way down to the magma, and the magma comes out of the ground, and all that kind of stuff. And so, it's a good surrogate for what we do, which is provide nuclear weapons to keep the world safe. It uses a lot of the same physics, and so we get to exercise things, computing technologies, codes, simulators, all that sort of stuff on problems that are of interest, but they're not necessarily classified. And so it's a good surrogate for us. And it actually has, interesting results for the country. If we wanted to try to deflect the asteroid, we'd need to know about the incidence rate. We might not be able to deflect it anywhere but put it in the ocean. And that might be the best thing to do, or it might be the best thing to do is to deflect it and put it in a desert somewhere. And so you can study all this stuff with simulations. You don't have to actually have a meteor hit the Earth to get it, right? Which is what we do, right? We simulate things that you simply can't test. And that's what we do for a living. You can't test nuclear weapons either, yet we have to certify that they work. And we have to certify that they'll work in horrible conditions and whatever they're supposed to do, right? And so that's our job. That's what we do. And this is a really good open example of how you do these things and the kind of data systems you need to push the data around, the kind of visualization systems you need to visualize it. You need surrogates to explain your problem to people so they can help you. And we need all help we can get.
Okay, well, thank you so much, Gary Grider of Los Alamos, Molly Presley of Hammerspace. Great to be with you.